Hello. So, we will be continuing our discussion on Ethernet, what we were discussing in the last lecture on data link layer phenomena under our this computer networks and internet protocol course, right. So, as Ethernet is one of the predominant technology in the layer 2 devices and omnipresent across the network. So, we already discussed some of the aspects. We will be trying to cover some more aspects here. So, it gives us a overall idea that how the Ethernet works, right. So, just to a recap slide, it was developed by Bob McAfee in Xerox PARC and his team in 1970. So, basic motivation from the Aloha packet radio network standardized by Xerox DEC in 78, and there are few standards which became pretty popular. 802.3 which uses CSMA CD, 802.3U for 100 Mbps standard Ethernet, and 803.Z 802.3Z which is for Gigabit Ethernet or 1000 Mbps Gigabit Ethernet, and it employs CSMA CD. So, just to give a Ethernet frame, last lecture also we discussed, but there are little bit maybe some ambiguity, but to clear it off, so the Ethernet frame is as far as the 802.3 standard constitutes a preamble. If you remember some slide, some of the literature mention preamble consisting of a 7 plus 8 bit, but as per the standard preamble is a 7 byte, 7 byte, SDF is 1 byte, destination MAC is 6 byte, source MAC is 6 byte, type is 2 bytes, payload max is 1500 bytes, 46 to 1500 bytes. So, if there is no payload, we should have at least a padding of 46, right. So, if I say the payload varies from 0 to 1500 bytes, the pad varies from 0 to 46 bytes, and we have a CRC check or FCS of 4 byte, right. So, preambles informs the receiving system that a frame is starting and enables synchronizations, right. So, that start of the for the synchronization, it says the receiving systems or informs the receiving system that a frame is starting. SDF or the start frame delimiter signifies the destination MAC address field begins at the next byte. So, it says that the next byte onwards the destination MAC address is there, or the hardware address or network address or LAN address, whatever we say. So, destination MAC address identifies the receiving system, source MAC address identifies the sending system, type identifies the protocol inside the frame, that means the next higher level protocol. Typically, for example, it may be IPv4 or IPv6, right, and data and pad contains the payload data, right, what it received from the higher level protocol, payload data, and padding data is added to meet the minimum length required for the field. So, the minimum length required for this field is 46 byte. So, the padding is added for that. If there is no payload, that means 0 thing is, if theoretically, then the padding of 46 will be there. If the full payload 1500 bytes are there, then it may not have any padding, right. And the frame check sequence, typically the CRC contains a 32 bit CRC redundancy check, which allows the detection of the corrupt data. So, that is the frame check sequence or FCS. So, this constitutes a typical Ethernet frame. A preamble 7 byte, SDF 1 byte, destination MAC address 6 bytes, source MAC address 6 byte, type 2 bytes, payload 46 to 1500 bytes, and payload plus padding. So, it should be at least 46 bytes and FCS of this, right. So, if we keep away this preamble and SDF, so we require 14 bytes at the beginning and 4 byte at the end. So, and these are primarily to more of synchronization and say that where the start of next address is there, and like sort of this, right. Now, how do I know the MAC address? Many of you might have tried. In Linux, there is a command called ipconfig. If you give /all, then it gives the MAC address of the thing, right. In Windows, there is ipconfig. In Windows, it is ifconfig. Let us just try if it works. Right. Now, if you let me see whether I can expand it. Okay, let us see. You can use the command called ifconfig, and you see here the MAC is MAC address is let me see ipconfig -/all. So, where is the MAC? Here is the physical address, right, 64.0.0.6a IC 1E63, right. So, this is the typical MAC of this particular systems where from where this I am using the systems, right. So, it is, and in case of this is this is ipconfig/all. Here also we have used this. Oh, okay, it is in the Windows only. In case of Linux, it is ifconfig, right. Anyway, that commands you can get easily. So, in other sense, what we want to say that you can basically get around this MAC address or the physical address of the things, and we see that is a 48 bit structure, 18 to 6, which signifies the MAC address of the particular systems. So, when we communicate, we require the source and the destination, and as let me repeat it, that when every hop, that MAC need to be resolved, right. So, when I hop from one system or one router or any network device to network device, every link, the hop, the MAC need to be resolved for the destination, and it is transmitted to the destination, right. So, the major challenge when we have a shared media is collision, right. That so, that is why carrier sends multiple access with collision detection scheme, right, when is for a wired media. Later on we will look at in some time we will look at the other mechanism for wireless media, where we have a, instead of collision detection, a collision avoidance scheme, because there are detecting a collision in a wireless media is much difficult, and that will come to that sometime later in this particular course. So, collision are caused when two adapters transmit the same time. Adapters sense collision based on the voltage difference, right. So, the how the collision is caused, when the two adapters, without knowing that both are thinking or both are sensing the channel to be free and communicate, and then it's collide, and there is a, once the collision is there is a fluctuation in the voltage. The adapter understands the voltage, like A is sending to B. So, at time 0 A starts, whereas more or less at the same time or after typical delta t time, the B starts, where also it sends this. So, somewhere here it collides, in between it collides, and then the voltage fluctuations, ripples among the things. Unless A gets a sense of that voltage difference, it gets A and B both thinks that there is a collision, it sends a jam packet and retransmit after some time, right. So, how can A know that a collision happens? There must be a mechanism to ensure retransmission on collision, right. Otherwise, we do not know that where the data, it gets sent and then there is no data where things are there, otherwise retransmission is there. If that is not there, so it is typically some sort of a connection or best effort service. You transmit and then forget that whatever has gone, right. So, A's message reaches B at time t. So, B's message from the B to A is 2t. So, A must still be transmitting at 2t. So, after 2t time it may know that there is a collision or not. So, 802.3 specifies max value of 2t to be 51.2 microsecond. Last class also we have seen. This relates to a maximum distance of 2500 meter between the host, which with a 10 Mbps speed in 0.1 microsecond, to transmit 1 bit to so 512 bits takes 51.2 microsecond. So, it takes point in 10 Mbps to transmit 1 bit, it take 0.1 microsecond. For in 51.2 microsecond, it will be some 512 bits or 64 KB 64 bytes of data to transit. So, the Ethernet frame must be 64 byte long, so that it can faithfully recognize or identify a collision. So, out of that 14 goes on the header, excluding that first 8 byte of preamble and SFD, and the 4 byte goes for the FCS or the CRC checks. So, 46 byte of the payload is minimum required, otherwise I cannot guarantee that whether I can find other things. That is why what we see that the payload length has been specified from not 0 to 1500, 46 to 1500 bytes, right. So, in other sense 0 to 1500 is the padding, or 0 to 46 is the, or in other sense 46 to 0 is the 0 to 1500 is the data, 0 to 46 or 46 to 0 is the padding of the data. So, that is the requirement of the of that particular payload field. So, if there is a collision, it sends a jam signal after collision to detect, to ensure that all hosts know about the collision or see the collision. So, it is a bit 48 bit signaling mechanisms. So, there is the same picture, there is a collision and there is a after 2t time A gets that information of the collision and then it goes on retransmission. So, if a collision is detected, delay and try again, that is the philosophy. It is not that immediately retransmit, delay, sense, try again, right, or try again in the sense again sense the channel and then pump the thing. So, first time choose k, how much time you will delay? K from 0 1, then delay for k into 51.2. So, second time choose k from 0 1 2 3, nth time k 0 to 2 to the power n minus 1, the maximum value of k will be 1023. This we have seen also, right. If the delay is not random, there is a chance that the source would retransmit in lockstep, and if it is a very small, then it is fine for small network, but it may be problematic, or large number of nodes will result in more collisions in a when k is small. So, from the receiver side, sender handles all access control, right. From the receiver is simply read the frames and acceptable address. So, address to host, address to broadcast, address to multicast to which the host belongs, all frames if the host is in the promiscuous state, right. So, this is the receiver things, right, if it wants to do in the receiver end. So, there is another, so what we have seen, sometimes we will down the today's talk itself we will see that gradually how it evolved, just to recap the things that how it evolved putting all those together. So, the with the increase of requirement of bandwidth and more bandwidth hungry applications, etc. So, we the overall graduated from fast Ethernet and Gigabit Ethernet. So, fast Ethernet which gives a 100 Mbps has technology very similar to 10 Mbps, uses different physical layer encoding 4B, 5B. We will see that when we will discuss about the physical layer sometime in this lecture series, and can be many NIC has both 10/100 compatibility. So, that means it switches based on the things, it negotiate and find out that where things will be there. So, other thing is the 100 Gbps or gigabit 100 Mbps or the gigabit Ethernet compatible with lower speed, uses standard framing and CSMA/CD algorithms. Distance are severely limited, typically used in the backbone and inter-router connectivity. So, it is a high speed things where the backbone and inter-router connectivity becoming cost competitive, that the cost is slowly coming down and it is becoming more viable. So, and that finally it need to be seen that how much effective bandwidth is realizable, that is also need to be calculated or need to be evaluated type of things. So, if we look at the Ethernet works best under light nodes, utilization over 30% is considered sometimes heavy nodes load, network capacity is wasted by collision, what I am talking that traditional Ethernet. Most networks are limited to about 200 nodes. So, specification allows up to 1024 nodes, but mostly when we say that within a particular network, then we have a 200 nodes, then we will see that concept of bridged LAN, that we have a bridge to connect the other LAN. Most networks are much shorter, 10 to 5 to 10 microsecond that RTT and around trip time. Transport layer level flow control helps reduce load. So, as we are talking about that, there are the other layers what they are doing, it is totally not keeping independently. The transport layer flow control mechanism may help in reducing the load. Ethernet is inexpensive, so to say, fast and easy to administer, right. So, Ethernet found to be cost effective, quite fast and easy to administer overall. So, it is a from the network administration point of view, it is always a good thing to look at the things. There are a few challenges, issues or with this Ethernet. That some of them as Ethernet's peak utilization is pretty low, right. So, it is low. Peak throughput works with more hosts. So, if you connect more hosts, that the throughput will fall. More collision need to identify by a single sender. Smaller packet size, more frequent arbitration. Longer links, collision take longer to observe, more wasted of bandwidth. If the link is longer, then it is a more collision takes a large time to observe. We have seen the 2 into T. Efficiency, sorry, there is a typo, can be improved by avoiding these conditions. So, see, these are maybe administratively controlled, and later on we will see that there are things which can be managed, we can manage with this Ethernet. So, this can be improved by avoiding these conditions. So, if we come to this overall evaluation of the standard Ethernet, so we have standard Ethernet, fast Ethernet, gigabit Ethernet, 10 gig Ethernet. Nowadays, we are talking about 10 gig Ethernet. We will see that there is a issue of bundling these things to larger bandwidth and so on and so forth. Mostly used for higher things are mostly used for backbone traffic, because neither the application nor the most of the devices can exploit that at that very high level, because I have a laptop with some 100 Mbps capability, connecting to a 1 gigabit switch is a wastage of the resources, right. And so, and secondly, all are not used, even your connectivity is at the 1 gigabit or 100 Mbps, finally your application may not be using more than 10 Mbps or 20 Mbps and type of things like that. So, it is again a wastage of resources, and whenever you go up on the scale on the speed, the cost increases, manageability becomes challenging, and it is a overall pressure on the backbone of the network. So, Ethernet addressing already we have seen, just to recall. So, each station on a Ethernet network or every system on a Ethernet network such as PC, workstation, printer, etc., which are network enabled, having a network interface card, has its own network interface card or NIC, right. So, MD systems like these systems what I am using here has its own NIC or network interface card, has a adapter to connect to the physical media. It can be wired connection, it can be wireless connection, it can be coax cable, it can be twisted pair, it can be fiber optic, it can be some wireless devices, Bluetooth, etc. NIC fits inside the station and provide the station with a 6-byte physical address, which is unique for every NIC ideally. So, typically like 17, 6C, 10, this is a typical thing, 6-byte address, right. And there is a scheme at the layer 2 level is of unicast, multicast and broadcast address, right. So, a source address is always unicast, right. So, when it is generating, it is always unicast. The frame comes from only one station. So, when you are generating a Ethernet or layer 2 frame, it comes from a one station. The destination address, however, can be unicast, multicast or broadcast. If the least significant bit of the first byte in the destination is 0, the address is unicast, right, or otherwise it is multicast, right. So, say this address, what is this 7? 7 signifies 0, 1, 1, 1. So, that means the least significant bit of the as we have seen, the least significant of the first byte in the destination address is not 0 in this case, 1. So, that means it is a multicast. Broadcast address is a special case of multicast in which all bits are 1. What does it mean? That all these are 1s. In other sense, this is a FF, 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 right, 6 FF, right. So, that is the that is the broadcast, a special case of multicast. Like here, if we have this A as the B, C, so A is a unicast because A is 0, 1, 1, 0, right. Anyway, last bit is 0 for this first this one. This the last bit of the first byte is 1. So, it is multicast and these are all 1s. So, that is broadcast, right. And if I have a address like this, there is maybe there is some typo because this is not representing directly here, because this is 47, it is not representing 47. So, just please recalculate this one. It should be some typo is there. Anyway, so what we mean to say, when we look at an address like this, it is decipher into the binary form, right. So, again I am repeating this 40, you just please check the representation. This 47 should be representing here, 20 representing here, 1 be representing here, 2e etc. 47 is not this representation, right, because 4 is 0, 0, 1, 0, 0, 0, 1, 0, 0 and 7 is 0, 1, 1. So, it should have been 0, 1, 0, 0, 0, 1, 1. So, that is a mistake here, just please correct it. Anyway, these are the bitwise representation and when it goes in this direction. So, the when it is sender is going and receiver is receiving, it is in this direction. Now, if we look at the standard Ethernet, already we have discussed. So, it is 10 base 5 bus thick coaxial, 10 base 2, it is again a bus structure with thin coaxial, 10 base T is the twisted pair, that is which allows star connects star type of topology, 10 base F is a fiber with a star topology, where 10 represent the speed of the thing. Ethernet evaluation, bridged Ethernet, dividing LANs using bridges, increase bandwidth and separate collision domains, right. So, if I have a large number of systems into the things, so there is a concept of bridged Ethernet, right. So, we put a bridge in between. So, what happens that instead of this one whole thing, I put a we can put a bridge here. So, these two LANs are now connected with a layer 2 device or bridge. What it does? It basically, as we know, layer 2 device divides the collision domains. The collisions are separate collision domains, and in effect it increases the overall bandwidth. So, this is the bridged Ethernet, where we have a better bandwidth things. So, if you look at your own network in your office or in your colleges, offices, and so where the number of networks are there. So, at least we have layer 2 devices which basically divide the collision domain, effectively increase the bandwidth of the network, right. Effective bandwidth of the network is increased, or in other sense the wastage of the bandwidth due to collision are reduced. So, that is a very standard practice to do that. So, divide LANs into bridges. So, we have the next phase, the bridge to switch. Switch can be thought of a what we can say a multi-port bridge. So, instead of one bridge dividing into two, I can have now a switch of 12 ports which is dividing into 12 domains, right. So, a separate domain which again can connect to the bridge. So, I can have a hierarchical structure of this layer 2 devices, right, which allows me to increase the effective better utilization of the bandwidth of the available network, right. It's like here we have one set of switches which goes on things, another a switch which connects a set of systems, this is a router or layer 3 device, right. So, it is a in this connection it is a full duplex connection, it can come to that. So, trans received is different. So, there is a not a challenge of collision, but effectively we can manage the things. And as you know that there are managed switches and type of things. So, we can basically understand and manage the switch in an effective manner, that how the switches can be managed and type of things in an effective, more effective manner. So, that you can have the overall health of the switch or management of the switch. Next one is a full duplex Ethernet, which is popular these days, which are mostly used these days in most of the today's network. So, full duplex network mode increases the capacity of the each domain to 10 Mbps to 20 Mbps. So, this is a full duplex, as we are showing the picture, that is full duplex. So, or it increases in somewhat double. In other sense, we have a separate transreceive line. So, they are not colliding with each other, in the transmitter and the receiver are not colliding with one another. So, that increases effectively. So, something 10 Mbps effectively increased to 20 Mbps. So, all our transreceive lines are different. So, in other sense, what we say in a full duplex Ethernet, there may not be need of any CSMA CD, because there is in a separate transreceive. So, there is a no collision per se, right. In a full duplex switch Ethernet, there is no need of CSMA CD method. In a full duplex switch Ethernet, each station is connected to the switch via two separate links, right. So, we have a trans line and a receive line. So, each station or switch can send or receive independently without worrying about the collision. Each link is a point to point dedicated path between the station and the switch, and the MAC layer becomes much simpler in this case, because it do not have to take care of all those things of the collision, avoid collision detection and type of things. So, in other sense, what we are saying these days, whenever this system is connected to a switch, it has a two separate line, one for trans and another for receives, right. So, in other sense, it has independently the trans receive things goes on, there is no collision. So, there is no need of CSMA CD per se. So, there is a MAC control layer. Standard Ethernet was designed as a connectionless protocol for MAC sublayer, right. So, if you look at the standard Ethernet, it was more of a connectionless protocol, like you transmit and as such you do not manage the thing. To provide flow and error control in a full duplex Ethernet, a new sublayer called MAC control is added between the LLC sublayer and MAC layer sublayer. Now, we need to have something which is a what we say flow and error control mechanisms within the Ethernet, right. So, if there is a error of transmission, that means you send the packet is not reached, you are sending acknowledgement, it is dropped. So, there is a both. So, that error hampers the overall flow mechanism of the things, because what we see the layer 2 is a hop by hop, but at the end of the day it has need to transmit across the thing, and in several cases it requires some sort of a flow control, error control mechanisms to ensure some sort of typical service level assurance or quality of services and type of things. So, first Ethernet already we have seen. So, was designed to compete with the LAN protocol if DDI or fiber channel. IEEE created the first Ethernet 802.3U, has a rate of 100 Mbps. So, goal upgrade the data rate to 100 Mbps, make it compatible with standard Ethernet, keep same 48 byte addressing scheme, keep the same frame format. So, there is no incompatibility, keep the same minimum and maximum frame length. So, those are kept. So, there is a feature in fast Ethernet is auto negotiation. New feature added to fast Ethernet is called auto negotiation. Auto negotiation allows two devices to negotiate the mode or data rate of operations, right. So, which mode and which data rate of operations to allow compatible devices to connect to incompatible devices to connect to each other, that will allow one device to have multiple capabilities, right. So, it can connect to 10 Mbps, 10/100, this type of things are possible to allow a station to check the hub's capability, like if it is a managed thing, then I can check that how much capability is there, and accordingly the station can transmit. So, hub or switch this is loosely used. So, it is so allow the station to check the switch capability. And finally, the what we are that next evolution of the thing is the Gigabit Ethernet, higher data rate of 1 Gbps in a full duplex mode. Gigabit Ethernet, there is no collision. The maximum length of the cable is determined by the signal attenuation in the cable. So, that is the only things which is there, and there are different variation of the things, and these days we are having 10 gig Ethernet and so on and so forth. So, these are some of the evolution of the things. So, what we do with this, we let us conclude today's lecture on overview or the overall that basic functionality or basic concept of Ethernet. So, now we will in the subsequent lecture we will look at more aspects of layer 2 or data link layer of this, but overall over our network layering or the OSI or TCP/IP layering. Thank you.